Next, we'll have our first keynote talk given by Karen Adolph. Karen is a professor at NYU with psychology, neuroscience, applied psychology, adolescent, blah, 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 many different affiliations. And she is a fellow of a bunch of associations. I try to remember, but it's very difficult to remember. And she has done amazing work, really eye-opening work in perceptual motor skill learning and development. And I'm so grateful that she can come and give us this talk. And one thing I want to mention is that she really has the envy of every academic researcher. Her research on perceptual motor skill learning has been continuously funded since 1991 by NIH and NSF. What a life. Let's welcome Karen.
I study behavior learning and development from head to toes. I study looking behaviors and facial gestures and manual behaviors, interactions with objects, postural behaviors, and locomotor behaviors. I study babies and children while they're alone and while they're engaged in social interactions, in lab experiments, and during natural activity in the home, in the United States and globally around the world. In the last talk that I heard by Jitendra Malik, he laid out his intellectual legacy that shapes his thinking. And so I'm going to take a page from Jitendra and do likewise. Since I was an undergraduate, the ideas of James Gibson shaped my thinking. So his ecological approach to behavior, the idea that perception guides action and action generates information for perception, that behavior always entails a reciprocity between animals and their environments, and all of this is captured in his notion of affordances. Eleanor Gibson was my doctoral advisor, and I am deeply guided by her ideas about learning and development. Today, I'm going to focus on the development of walking. So I'm going to tell my story using walking like a case study. But I think that my arguments pretty much hold for every kind of foundational behavior. And every behavior involves learning, development, and control. So walking, for example, starts something like this: the baby who can barely keep balance long enough to take a few steps. And then 100 days later, it becomes something like this. This is a baby who can steer and navigate and carry things from place to place and get where he wants to go. So for walking, what's learned? What develops and what's controlled? What has to happen so that babies and adults and animals or robots, whoever, can safely navigate the world and engage in everyday tasks? Functional behavior is not about doing the same things over and over. It's not like taking repetitive alternating steps on a motorized treadmill, or even taking alternating steps in a straight path over flat ground. Walking involves getting upright and keeping balance, of course, but it also involves taking omnidirectional steps and starting and stopping at will. Functional walking involves modifying ongoing gait patterns to suit changes in the environment. And functional walking involves perceiving affordances, detecting change in the environment, exploring to generate information, finding alternative means to achieve your goals. Functional, adaptive, flexible behavior is required at every point in development. You always have to gear your behaviors to changing conditions, right? Changes in the local conditions, but how you do it differs across development. For 30 years, I've been testing infants on crazy apparatuses like slopes and bridges and drop-offs and gaps and ledges and apertures they have to walk through and overhead barriers and underfoot barriers. And all of that was designed to understand how babies acquire functional, adaptive behaviors. So what's learned? What develops and what's controlled? How does that work? And how might infant data inform AI? And how might AI enrich our understanding of behavioral development? Well, functional walking has 6 critical components, and all of them involve learning, development, and control. So I'm going to talk about them one by one. Walking involves the ability to move the legs. Leg movements appear prenatally. There's prenatal leg movements in human infants, in rat pups, and chicks, in every animal that anyone has ever studied. Fetuses can alternate their legs, left to right, left to right. They can move each leg in isolation. They can move both of their legs simultaneously. And there's learning and development and control, of course, but it's brainstem control. This is pretty divorced from psychology. Waking infants move their legs and feet, but spontaneous motility is just leg movements. It's a component of functional walking. This is not functional walking. And like awake infants, sleeping infants move their legs and feet. But just like awake motility, these kinds of twitching movements are controlled subcortically. And if you hold a newborn infant upright, they move their legs, and some of their leg movements kind of look like walking. This was actually my baby, and although my baby was very talented and extremely beautiful, anencephalic infants can do this. Decerebrate cats can do this. This is not walking. Moving the legs is not functional walking. Fetuses can move their legs. Newborns can move their legs. They can move them while they're awake. They can also move them while they're asleep. And newborns can take upright steps if you hold them upright. But anencephalic infants and decerebrate cats can move their legs if you hold them upright. It's not walking. Supporting body weight and keeping balance are critical components of walking. And compared to moving the legs, these are actually kind of hard. When they first can stand, infants collapse due to insufficient leg strength. You can increase their leg strength through exercise, but a lot of what develops is physiology, not psychology. Even quiet stance is a struggle, because if babies lift an arm or tilt their head, they fall over. A lot of supporting body weight and maintaining upright balance is more about physiology than about psychology. Human infants actually have relatively few opportunities to practice upright balance until they can support their own body weight. However, balance control is likely more advanced before you can see it because of the body weight thing, because when body weight is reduced by a harness or by a caregiver's hands, then balance control is revealed. But nonetheless, infants have a lot to learn about anticipatory balance control, about using perception to control their balance, because they will still fall if they try to do anything, like lift their arm or tilt their head. The ability to produce varied gait patterns, this is a really critical component of functional walking. Now I'm talking about the ability to take omnidirectional steps along varied paths to generate bouts of different lengths by starting and stopping at will. In everyday life, no one walks on treadmills. Functional walking is not comprised only of continual, regular, alternating steps along a straight path. Instead, it's a lot of starts and stops. Some are longer bouts, but there's also really short ones. And they have varied step lengths and varied speeds and omnidirectional steps that take babies or anyone, people of all ages, along straight paths and also curved paths. Functional walking requires steps in every direction. Most of infants' walking bouts contain steps that are not forward. Their steps are omnidirectional. That means some are forward, some are backward, some are sideways. So I'm going to play it at half speed so you can really see what I mean. This baby takes 1, 2 sideways steps, then 1, 2, 3 forward steps, then 1, 2 3 backward steps. Less than 20% of infants' bouts are only forward steps. Most bouts have a mixture of step directions or no forward steps at all. And that's true across development. So that means that taking a backward step or a sideways step, it's not a characteristic of poor walking skill. It's not a consequence of poor motor control, because babies are taking omnidirectional steps when they first start walking. They're taking omnidirectional steps 9 months later when walking skill is already beginning to asymptote. Functional walking requires varied path shapes, so people can get where they want to go. The squiggly blue line is the path of one 13-month-old in 10 minutes of natural activity in a lab playroom. Infants repeat things, but they're never doing exactly the same thing. As Nikolai Bernstein, the famous movement physiologist, put it, it's repetition without repetition. So babies can walk straight paths and they can walk curved paths. Relatively few walking paths are straight. Most of the paths are curved. And there's curved paths across development, curved paths in new walkers, curved paths in experienced walkers. That means that the two sides of the body are doing different things. It's not symmetrical. It's not doing the same thing. These are timelines of infant walking across 2 two-hour home visits. The red bars are the time that infants are walking. Each row is a different baby. Walking is time distributed into bouts of different lengths for every baby at every age. And that means that functional walking is a lot about starting and stopping, not continual stepping. So watch this baby's right foot. She's just standing there and then takes a step. That's it. That's the whole bout. Short bouts are common across development. More than 30% of bouts have only 1 or 2 or 3 steps. Babies can take longer bouts, and they often do, but a lot of the time it's only 1 or 2 or 3 steps. All those little bouts add up. This graph shows the accumulated number of steps per hour plotted against days of walking. Each symbol is one infant's spontaneous walking in a lab playroom that's filled with toys. So babies walk a lot. On average, 2,400 steps per hour. That's like 14,000 steps in a day. We see the same thing in new samples of infants tested in a lab playroom set up with different toys in a different layout. We see the same thing when we record walking in infants' homes. We see the same thing in new studies of natural activity in the home. Infants produce immense amounts of varied steps, varied paths, and varied bouts during everyday activity. Varied walking, varied gait patterns, that is not due to a lack of control, because infants' walking is varied when they first begin walking, and they're still doing it 9-10 months later after walking skill begins to asymptote. Varied walking is the behavior that infants are learning to control. But even after babies can support their body weight and keep upright balance and produce varied steps and paths and bouts, their walking is filled with errors. Babies fall all the time. They fall when they try to sit down. They fall when they try to stand up. They fall all the time. On average, infants fall 40 times for each hour that they are in locomotion. Babies fall a lot, but they don't care. Their parents don't care. Infants' everyday falls are so trivial that they rarely fuss, and caregivers rarely show any sign of concern. 91% of falls are completely uneventful. And babies are back at play right away. Even after a big fall, this baby is back at play within 3 seconds. On average, infants recover from their falls within 2 seconds. And infants don't decrease their walking or stay away from the objects or the places in the room that were associated with their falls. This baby fell 15 times with this stroller. in like 20 minutes. But the falls didn't discourage her from walking with the stroller. Across infants, they walk just as much after each fall as they had done before the fall. Now, one factor that mitigates the impact of falling is the size and shape and composition of infants' bodies. So infants are short and they're low to the ground and they're padded with baby fat. It's like they're built to fall. The potential energy generated by infant falls is 18 times less than if babies were adult-sized and walked at adult speeds. So what do infant falls tell us about learning development and control? Varied walking is interrupted by frequent falls. It means infants are losing control as they push the limits of their newly emerging skills. But that's okay because errors are generally trivial and it doesn't dissuade infants from practicing. In fact, infants' naturally varied practice regimen actually facilitates learning development and control. So we use simulated robots to test whether all that crazy varied gait patterns in infant walking is really a good way to learn. This is a simulated robot being trained to walk different paths in Peter Stone's lab. And then the success of the training is evaluated with robot soccer. Why soccer? Because it's kind of like real life. It's unpredictable, it's novel, it's variable, there's other active agents, everybody's got goals. In Tournament 1, we asked how training robots on geometric paths would compare to training robots on real baby paths. Short answer, babies win. Across 1,000 matches between each pair of teams, babies showed the largest average goal difference. In Tournament 2, we used machine learning to cluster 75 infants' paths into 5 groups based on the variability of their walking. That purple team number 5 was the most varied on all the measures. Tournament 2 showed that more varied experience leads to better functional consequences. It leads to more wins in 1,000 head-to-head matches of RoboCup. We also used simulated robots to test whether a penalty for falling is good or bad for learning to walk. When we tested robots on the same walking path that they were trained on, we found that a lower penalty for falling leads to better walking performance. Robots that were trained with 0 penalty for falling walked the farthest on the paths they were trained on. And when we tested the robot's skill transfer to novel, untrained infant paths, we find that the robots trained with 0 penalty for falling walked the farthest on untrained paths. Simulated robots show that variability and a low penalty for errors are beneficial for learning. Variability is a feature of motor behavior. It's not a bug in the system. Why is varied walking so important? Because it ensures that the system keeps getting new inputs from new experiences. It pushes the system forward in development. And a low, not a high penalty for falling, or really any errors, is better for learning and transfer. Why? Because a low penalty ensures that infants or robots maintain a high motivation to keep practicing. Learning comes from positive, not negative reward. And one more thing about rewards. What motivates a baby to get all that practice? Why do they move? Well, one common sense hypothesis is that infants move to get to the people and places and things that they see. So to study whether where infants look influences where they go, we put head-mounted eye trackers on babies. If infants really move to go to a destination, then they should look at something while they're stationary and then go to it. So here's what about like that would look like. While the baby is stationary, he sees that red ball, and that's the destination, and he walks to the ball. Turns out, destination-directed bouts are pretty rare. It's also possible that infants discover something while they're traveling. So in this kind of like a discovery bout, an infant is looking all around and looking at whatever, and then they see something like maybe the saxophone, and they start walking and they see something else like that green alligator, and that becomes a sort of found destination. Discovery bouts, also rare. What's happening most of the time? Most of the time, infants start moving while they're looking all over, and then they just move, walk, and then they just stop in the middle of the floor, beyond arm's reach of any recognizable person, place, or thing. Most of babies' bouts don't involve a destination at all. Now, we figured if it's really true that objects like toys are not needed to instigate locomotion, then infants should move just as much in an empty room as in a room filled with toys. So we tested infants playing in a room filled with toys, actually toys that were designed to encourage locomotion, and we compared their behavior to infants in the same room with all the toys removed. We find infants walk just as much in an empty room as in a room filled with toys. They spend the same amount of time in motion, they take the same number of steps per hour, and they travel the same distance per hour. And actually, they're moving a lot. This is 4,000 steps per hour. And in both conditions, they go to the same low percentage of destinations, only 30%. In the toy room, infants mostly went to toys. And in the empty room, infants went to their caregivers and to features of the room. So if you want to be the best thing in your infant's life, take everything else out of the room. 70% of the time, infants were just running around. What differs is that infants in the toy room spend less time near their caregiver, and infants in the toy room explore more of the playroom. The difference is really clear when you look at individual infants' paths. These are paths from one infant in the toy room and one infant in the no toy room. The black dot is the caregiver. She just sits, or he, in a chair. These two infants took a similar number of steps, but they covered really different amounts of area. Infants in the toy room travel all over, but infants in the no toy room repeat their paths. Here's all the infants' paths, ordered by the amount of area that they covered. Infants in the toy-filled room cover more area and the same amount of steps. So movement achieves goals? Of course it does. But for typically developing infants, movement is also its own reward. And infants sometimes move to goals. They could be goals imposed by their caregivers or by researchers, or it could be goals of their own choosing. But infants also move spontaneously with no goal in sight and no goal in mind. But all of that movement leads to enhanced opportunities for learning and for improvements in walking skill. All right, here's all the components of functional walking. So remember, moving the legs begins in utero, but supporting body weight, maintaining upright balance, and varied gait, all of that could happen in a totally open field, right? But gait modifications and perceiving affordances, that's about walking in a varied environment. And functional walking happens in a varied environment that's cluttered with variations in the terrain and obstacles in the path, not in an open field. So, to my mind, it's not until babies can modify their gait and perceive affordances for walking that babies really can walk. So let's talk about gait modifications. On shallow slopes, like this one, experienced walking infants walk straight down with wide, evenly spaced steps. But on steep slopes, infants begin modifying their steps before they go over the brink, and then they break their forward momentum all the way down the slope. On wide bridges, infants run straight across with long, evenly spaced steps. But on narrow bridges, infants modify their gait during approach And then they inch across the bridge, taking really short, really slow, really narrow steps, sometimes like lead follow steps like that, until they get themselves near the end of the bridge and they can safely step off. Look at infants' gait modifications on slopes and bridges. Babies take shorter, slower steps on the slope and on the bridge. But the more important thing is that infants are learned to modify their gait prospectively, not reactively. That cluster of footfalls right at the brink means that infants are modifying their gait before they step onto the slope, before they step onto the bridge. With George Pavlokos and Peter Stone at UT Austin, we're modeling infants' full body pose with a mesh to get the XYZ coordinates of each limb, each step, at each video frame. Our idea is to use the precise coordinates of infant movements to train and to test robots in simulation. So we can do dozens or whatever, hundreds of randomized control trials with simulated robots that would be impossible to do with real babies. So we can test which aspects of infants' natural training curricula are actually leading to better functional walking. Infants learn to modify their ongoing actions. They change how they move to suit changes in local conditions. And their modifications are prospective, not reactive. They're planning ahead of time. They're not, adjusting after the fact. And the only way you can do that is to gather perceptual information to plan ongoing behaviors. The last component, the thing that makes walking truly functional, is perceiving affordances for action. Now, in 1957, Eleanor Gibson invented the visual cliff. This is an illusory drop-off. So the cliff is covered in safety glass, so it looks like a cliff, even though it's perfectly safe. Turns out that baby humans can feel the glass, so after one trial, they figure out that the drop-off is perfectly safe. So you can only test a human infant with one trial on a visual cliff. So in the 1990s, under Gibson's tutelage, I began testing infants on real drop-offs with no safety glass. Instead of the safety glass, an experimenter follows alongside the babies to rescue them if they fall. With this procedure, you can test babies over dozens of trials per session. You can do psychophysics. This is our adjustable drop-off apparatus in my lab. It can have really small drop-offs, like a step, that afford locomotion, or really, really high drop-offs, like a cliff, where locomotion is impossible. From infant's view, it looks something like this. Newly walking infants do not perceive affordances. So novice walkers will repeatedly attempt to walk down drop-offs that are beyond their ability. They seriously do. Even on a 90-centimeter drop-off, they plunge over the edge. Novice walkers behave as if they have no clue about the limits of their own abilities. After several months of walking experience, infants now can perceive affordances. They can perceive precisely within 1 centimeter of accuracy whether a drop-off is safe for walking. Experienced 18-month-olds perceive whether the drop-off's too high for walking, and if a drop-off is too high, they stay put or they find an alternative. Here's data. 0 here is the largest drop-off that each infant could navigate. So these data are normalized, right, to each infant's ability. The negative numbers are drop-offs that are smaller than the threshold, so these are safe. These are the drop-offs that are like a step. And the positive numbers are drop-offs that are larger than the threshold. These are risky drop-offs. These are, essentially a cliff. And then there's a 1 centimeter really easy drop-off and a 90 centimeter visual cliff-sized drop-off. The blue curve shows that novice 12-month-old walkers vastly overestimate their abilities. They will attempt to walk over impossibly high drop-offs. These babies had not yet learned to perceive affordances. In contrast, 18-month-old experienced walkers precisely perceive affordances. Experienced walkers are actually probability matching. They're matching the probability of attempting to walk with the conditional probability of success. The same story goes for other obstacles. Novice walkers don't perceive affordances for walking down slopes. They will attempt to walk down slopes that are too steep for their abilities. But experienced walkers can precisely judge which slopes are within their abilities and which slopes are not. This graph shows infants' attempts to walk down safe and risky slopes. Novice walkers attempt to walk down impossibly steep slopes, but experienced walkers perceive affordances based on their own abilities. We see the same thing on bridges. Novice walkers do not perceive affordances on bridges, but experienced walkers precisely perceive which bridges are within their abilities and which are not. This 8-centimeter bridge is the current world record of baby bridge walking. Here's the data for bridges. Novice walkers attempt more than experienced walkers at the risky increments. Now, what makes these data especially compelling is these are actually the same babies on both slopes and bridges. So here's a novice walker in both tasks. First, you'll see her on an impossibly risky 50-degree slope. And here she is on an impossibly risky 8-centimeter wide bridge. Same baby, both tasks. Here's all the novice walker data together. Infants show similar behaviors on both slopes and bridges, especially at the risky increments. For experienced walkers, their perceptual judgments are even more consistent at the risky increments. That means that infants who know whether a slope is risky also know whether bridges are risky. All right, after 30 years of research, one thing is clear. Functional, adaptive, flexible human behavior is not innate, it's learned. Infants have to learn to perceive affordances. With each week of everyday walking experience, infants' perceptual judgments become more and more accurate. What are infants learning from everyday experience? Well, they're learning to perceive and to exploit new possibilities for action. They're not learning specific things about cliffs and slopes and bridges because these test apparatuses are novel. They're designed to be novel, right? And part of the learning includes discovering and honing the right exploratory actions to generate the right perceptual information. Babies are learning to learn. Well, what about precocial animals? Animals that supposedly can walk right at birth or shortly after. Here's a baby goat peering over the brink of Gibson's visual cliff. Images like this and anecdotes led people to believe that precocial animals like goats can perceive affordances shortly after birth. But images and anecdotes and YouTube videos are not robust experimental data. So we're collecting robust experimental data. Now, just like baby goats and horses and chicks, pigs, it turns out, are precocial. These are 13 baby pigs. It's 6 to 8 hours after birth. That was as fast as we could get them off the farm. A couple of them are sleeping. They're not dead. But most of them are moving their legs. They're supporting their body weight and maintaining upright balance. They're producing varied walking. So the question is, can precocial animals also modify their gait and perceive affordances to cope with a varied environment? With Jesse Young and Whitney Cole, we're testing whether precocial animals perceive affordances. Just like with human babies, we lured them with snacks and toys and sweet encouragements. And as you saw with the babies, a trained experimenter rescues them mid-fall. On day 1, we tested 13 piglets 6 to 8 hours after birth. 13 out of 13 piggies plunged over the edge of a 1-meter high drop-off. Okay, I'm going to show you pig number 1 in the video. Here's piggy 1. All right. Here's pig 2. Here's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All of them. On day 3, 11 out of the 13 pigs plunged over the 1-meter-high drop-off. Here's pig 1 again. I don't know how to turn the sound up, but I wanted you to hear it because it's amazing. It's just like you could just replace the pig with a baby, except pigs like a poopy blanket and babies like, we'd use a non-poopy blanket. Anyway, here's all the rest of the pigs. Only pig 5 and pig 13 showed any evidence of perceiving affordances. So I'm going to show you pig 13. She actually turned her back on the drop-off and avoided going for the whole 60-second trial.
Yeah, I know. There's some food here, though. Here's some food here. We love the food. Hi. Not that horse, though.
All right. Walking skill improved for all the pigs, but for most pigs, perceiving affordances did not. Most of the pigs could walk over higher drop-offs on day 3 than they could on day 1, but for 11 of the 13 pigs, their ability to perceive affordances did not improve. This is the first real evidence, and here, this is based on psychophysical procedure. This is the first real experimental evidence about whether precocial animals perceive affordances at birth. Clearly, they do not. So we only could test the pigs for 3 days, long story, but at some point, juvenile and adult pigs learn to perceive affordances. So they perceive whether they can jump over chasms, they perceive whether the terrain affords walking. Precocial animals, at least pigs, do not perceive affordances shortly after birth. Even precocial animals require learning. And I say, how could it be otherwise? Animals cannot know their bodies or the environment without experience living and moving in their bodies in the environment. Babies differ from robots in a really important way. Robots' bodies don't change, but infant behavior develops in a changing body with changing skills in a changing world. That means that learning is always occurring in the larger context of development. Infants' bodies grow, and their growth is rapid, and it's episodic. Like they can grow 2 centimeters in height in a 24-hour period. Infant skills change dramatically, especially for posture and locomotion. And how children can move affects their potential access to the environment, what they see and what they touch and where they go, their visual, manual, and whole body access to the environment. Because infants' body skills and environments are developing, development constrains the input. It's not William James's blooming, buzzing confusion because development constrains the input. It's sensible, manageable, ingestible input. A nice example is the transition from crawling to walking. Walking literally brings more of the world into view. Walking gives infants a better vantage point because of how the head just physically connects to the torso on the human body. While crawling, their head naturally points down, but while walking, their head points straight ahead. For crawlers to position their head forward, they have to crank their heads up as far as their neck can go. Here's a crawling infant's view of the world. While crawling, infants' heads point down, not forward, so they're mostly seeing the floor right in front of their hands. But in a walking posture, the entire room is visible. We're testing infants longitudinally from 2 months to 18 months to test how developing skills change infants' visual, manual, and whole body access to the environment. At each visit, we observe the baby in the same room with exactly the same room setup. The playroom has lots of interesting stuff to see and objects to touch and places to visit and stuff to go to. At each session, we put infants down on their backs on the gridded mat in exactly the same spot. The caregiver sits in a chair and is occupied on their phone, and then babies have 10 minutes to do whatever they want to do. When babies are really young, they can't even get off their back. When they can sit up, they can also sort of scooch around, and their access to the environment starts to expand, and they can explore the mat and the toys that are nearby. When babies can crawl, they can go off the mat and explore a larger space in the playroom, and they can play with a lot more toys. And when babies can walk, they can go anywhere in the room, so they can go more and see more and do more. We've rendered the room in 3D, so now you're looking at a rendering, not a video. And with the rendering, we can manipulate the room to see it from every angle at every moment. We can analyze every visual, manual, and whole body contact with the environment with pretty much centimeter precision. Here's what a rolling baby can see. The red line shows the direction of gaze from ceiling to a bit of the walls, and then finally to the floor when the baby rolls over. The red cone here shows everything in that rolling baby's field of view. The white regions show the whole history of that baby's visual exploration. It's basically like a partial sphere around the mat. Here's the tactile input. Green shows one hand, pink shows the other. So the rolly baby can touch just stuff in a little area on the mat. And here's everywhere that the baby's whole body went. In contrast, this is a walking baby. Walking infants are going everywhere and seeing everything. They're up, they're down, they're all around. Here's the visual cone to capture everything in the field of view. And here's the history of what a walking infant sees in 10 minutes of spontaneous activity. The green and the pink show what the infant's hands touched. And here's the baby's path through the room. These data summarize where infants go as they acquire more skills. At first, they don't go anywhere. And then they cover every inch of the room. As infants acquire more motor skills, they travel longer distances. They visit more unique areas in the playroom. This is a bird's eye view of the playroom. Here's the wall that divides the mat from the rest of the room. So based on the location of that wall, we divided the room into several places. The mat, where infants start off, within arm's reach of their caregiver, the area near to the caregiver, the area far from the caregiver, but where the caregiver is still visible to the baby, and the area far from the caregiver, where the caregiver is no longer visible to the infant. As infants acquire more skills, they visit more places, including the areas far away from the caregiver. Even though infants don't spend long periods of time out of sight of their caregivers, mobile infants make lots of visits to the far regions of the room. The arrows show the number of transitions between areas. So behavior gets learned and controlled, and it's developing in a changing body with changing skills in a changing world. Bodies and skills constrain interactions with the environment and filter information from the environment. Because bodies and skills develop, the environment also develops. And across development, infants in the same environment do not experience the same environment. I'm going to end with a pitch for open video sharing. Sharing videos will speed discovery about motor learning, control, and development. And that's where Databrary comes in. Databrary is a web-based library for research videos. It's designed for the secure, ethical, open sharing of research video. Video uniquely demonstrates procedures and findings. This whole presentation used video as demonstration. Video data are uniquely suited for reuse. You could ask new questions that the original researcher had never even imagined. And Databrary manages and preserves videos indefinitely. As of, a few days ago, Databrary had 1,816 authorized investigators from 808 institutions around the globe and was serving up 123,000 hours of shared video. To capitalize on the richness of video, you need tools. So we created the DataView human annotation tool. This is software you can download to your computer. It's offered free and openly to researchers. This is really important because human annotation is still the gold standard for reliability and validity. But as you saw, computer vision can do amazing things like even track people's head and eye position and estimate what they can see in 3 dimensions. What are the benefits of video recording, video annotation, video sharing, and video reuse? I think it's pretty huge. It's increased transparency and reproducibility, and it will speed up scientific progress. So go register on Databrary. All right, summing up, how does behavior develop? Infants acquire flexible, functional behavior from immense amounts of time-distributed, varied, imperfect practice during everyday activity with a changing body and changing skills in a changing world. Basically, infant humans, infant piggies, infants of all the different infants are learning to learn. They're learning how to generate the requisite perceptual information from moment to moment that will specify which behaviors they can and can't do and how to do them. As a science, we have the paradigms and tools and technology and even the infrastructure to really understand behavior, to understand what's learned, what develops, and what's controlled. We've just got to do it. And I'm going to give the last word to this wonderful clip of a baby. This is Deb Roy's baby taking his very first walking steps.
Hey, come here. Can you do it? Oh boy, can you do it? Now he's walking.
So wow. All right, thanks. Yeah.
Any questions?
How much is the gap from the hardware, for example, like human, we have span, humanoid, many humanoid don't have span, and software, and the interaction between software and hardware. And what is your suggestion on people working on robotics mobility and interacting with the environment?
Okay, I'm going to repeat the question. Amazing talk. And there's still a large gap between, biological systems and AI, humanoid, whatever, robotic systems. And some of the problem is in software and some is in hardware. And how much do I think it is? And how do we close that gap? Is that about it? I don't know how to speak to the hardware because I know you guys have like soft robotics and whatnot, but every time I see things that you're excited about, I'm just like, yeah, an 18-month-old, human infant can just wipe you up, So So I've put my money on simulated robots, and I think also because so much of the algorithms are being done in sim and then put into real, if I understand correctly, I think that makes a reasonable amount of sense. It's I think that both fields need to take insights from each other. So, the behavioral researchers need to stop waving our arms around and saying it's learning to learn, and make it formalize it. And you guys have embodied AI that's it. That's perfection. That's the way to actually test a theory, right? But I think that you have to take a lot from what people know from actual behavior, and especially from behavioral development, where learning and development and control are all mixed up in this just beautiful symphony, and it's totally tractable. I'm totally serious. I mean, there's 123,000 hours of shared video. Go take advantage of that instead of scraping stuff from social media. There's the diversity of what just any species can do. It's right there. And, and instead of your doctoral students sitting around and going well, I'm going to come up with this that was mean, I'm sorry. Instead of a doctoral student saying, I'm going to come up with this amazing training regimen that I pulled out of my butt and then train my simulated robot, whatever. Let's find out what real animals really do, and maybe take that as guidance, because they're really doing it, and they're doing it pretty freaking well. Okay.
Any other questions?
In your talk, you mentioned about the learning kind of diminishes after you have the perception about the environment and those kind of things. What makes it to stop the learning process?
What makes them?
The learning process. Remember the room, whatever the area, the environment that you're testing all of these things, right? It is limited. How do you explore beyond the room, whatever the box?
I love your question. That's a beautiful developmental science question. His question was, why don't they stop? What keeps pushing the learning along? It's a great mystery in developmental science, and that's where a lot of the hand waving comes in. Maybe it helps to build in positive reward for just, I don't know if formalizing it actually helps. And this isn't just human babies. Every animal that people have studied, the puppies chasing their tails and the colts gambling or whatever, all that stuff. Why? Why are you wasting so much energy? They're totally inefficient. Their mother has to go out and kill something to make more milk to feed this animal that's just, and it's just a baby. It can't possibly know this is going to be good for me in the long term, right? So what I tried to show is that animals are just behaving. As soon as they have muscles that are innervated, they're behaving. They're behaving before they're born. They're behaving. And that behavior is giving them feedback, and it's shaping their little brains. Those twitching, my boyfriend actually does this. It maps the somatosensory cortex, all those little twitches while asleep. It's not useless, right? So we don't know until we test it with a formal system like robotics, which are the things that are just not hurting anything, but they're not helping, and which are the things that are really helping. Babies actually just do whatever it is they can do. They're not doing a checklist like a researcher, I really want to hit my crawling milestone. What's the criterion for that? They just do whatever it is that they can do. And then here's another thing, if you can do it, engineers out there, build a system that can fail. Language learning, babies are horrible. All they do is make mistakes. They mispronounce. They say the wrong things. It's horrible. And I'll tell you what, you can't use language to tell a baby, twist the lid counterclockwise. All they understood was nothing, maybe. Nothing in that, right? So they just try. And there's no penalty because nobody goes bad baby, wrong grammar, baby. There's no penalty. You just make them do stuff. And they do stuff, and then they just some of the time push their limits, and they'll still keep making mistakes, and no one cares. So that's my answer, which was very hand-wavy, literally. But thank you.
Let's take one last question.
Right, fascinating research. I wonder how much, throughout your experience, how much of a role does vision play in this? Like in the visual cliff, seems like if you can't visually perceive the cliff, there's no stopping, right?
Yeah,
and
yeah,
then
yeah.
in the exploration, there seems like if you can't see it, maybe they won't explore that much. I'm just wondering like how much of a role vision play in all of this. Thanks.
Yeah, I love that question too. So the question is, what is the role of vision and how big of a role does vision have? I've never studied babies who are blind or have limited vision, but everything is delayed in babies like that. But what I have done is measure what they're seeing and when they're seeing it. And, you know, vision is just an amazing perceptual system. I love vision. I don't know. Vision plays a major role. And you're absolutely right. If you can't see the edge of the drop-off, then you're... Oh, I have another answer that I want to say that I might like better. All right, so there's all different ways that we have to generate information, right? And we don't do all the information generating exploratory procedures all the time, all at once, right? Like a blind person has to have like a feeler out in front of them, a cane or something, because they don't have a long distance sense like vision. For human infants, vision is their long distance sense, and especially for large, slow movements like locomotion, vision comes first. For fast movements like manual actions, when vision doesn't come first, they make mistakes. Without vision, your brain doesn't know what to do, and then your brain can't tell your muscles, and then it's just this whole real-time cascade of bleh. And I know that for a fact, because head-mounted eye tracking, EEG, motion trackers, you know, it has to happen like that. You need, you know. But it kind of ramps up. So, you know, you're walking, I don't want to leave the microphone, but you know, you're walking along the stage, and then vision tells you there's a thing, and so then you start to modify your gait. And then you do the more expensive kind of exploratory behaviors like touching or getting, you know, proprioceptive haptic information, et cetera, testing, blah, 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 right? You don't do everything all at once. Think of a bat. So bats, you know, they use echolocation, but they're just like doing like their bat noise. And then like, you know, ping comes off of an obstacle, and they then turn their ears like that, and then they start emitting at high rate, you know, because now they know, but you don't walk around like, because like, you don't need to. So you just, so vision is really important. Having a long distance sense is really important. For humans, it's vision.
Okay, let's thank Karen for this amazing talk.